Cool. So today's lecture is going to be about manometers. I'm not a big fan of manometers. There aren't many left. um, when I was in the 2000s, there were still manometers like on fume hoods in areas where you needed to measure pressure but not accurately and cheaply. Well, not accurately but cheaply. And now it's so cheap to make pressure sensors that it makes, and to read pressure sensors, it makes almost no sense to use a manometer. Um, None whatsoever. So why do we still teach it? Well, we still teach it because it's excellent practice for two things. Two things we just taught you. So in the previous section, we just taught you about the first rule, rule number one. Whoops. Rule number one of hydrostatics. If you remember that, it's that at a single point in a stationary fluid, the pressure is the same in all directions, right? And also, this rule, delta P is equal to rho G delta H, or as we like to say, P1 minus P2 is equal to rho G H2 minus H1, which basically says that the pressure in a fluid only changes with height, and it changes linearly with height, where the proportionality constant is rho times G. More importantly, as we learned in the last lecture, what's really interesting about this is that the pressure in a fluid is only a function of the height of the fluid above it, not the amount of fluid. So if you guys remember Pascal's barrel busting, where somebody presumably, well, we know the woman did with a giant glass flask, but you can burst these things with a very thin capillary tube full of water, as long as the capillary tube of water is high enough, because that's all that matters to produce the pressure necessary to break something. Great. And then we also applied it to our semester-long design project and discovered that a 60-kilometer tall column of water simply cannot be contained by a tube of steel by any means, but possibly by tubes of some more costly material, but we're talking about a 60-kilometer tall pipe. It's got to be cheap. All right. So we're going to practice this now using something called manometers. And what are manometers? Manometers are a way of using the variation in height of a fluid to measure pressure. That's it. So, for example, if we have this simple example here, let's say we want to know the pressure at A, and we know the height at C and the height at B, right? So the first thing is, the question you should always ask yourself when you're about to solve a problem is, what model should we use, right? So now we're trying to relate heights to pressure because we want to figure out the pressure at A, and we only have one model for that. Honestly, we only have one model right now, period. But we're going to use the model that P1 minus P2 is equal to rho G H2 minus H1. We're going to call that equation 1. Let's talk about our assumptions real quick for this. Our assumptions are that the fluid has to stay still, and also that rho is equal to a constant. We also say that G is equal to a constant, but I don't know. Has there ever been a class where G has not been a constant for you guys? I don't think so. Great. So we're going to use rule number 1, and we're going to use this delta P equals rho GH. So the first thing we're going to say is that pressure at B minus the pressure at C is equal to rho, and oh, by the way, this is this didn't get copied to this version, but this is oil in here with a density of rho oil. Rho G, and then we got to use H's. We have to put in some H's, right? And to do that, we need to put in a coordinate system. I just drew this for you, but you need a coordinate system in order to actually measure distances. So we're going to say that our coordinate system looks like this, where this is X and this is Y. This is our datum. This is where Y is equal to 0. So A and B are both at 0 and C is at YC. So we're going to say this is equal to rho G times YC minus YB, but YB is equal to 0. So this is equal to rho G YC. And then we're also going to use gauge pressure. And it's good. Remember, like I said, you're trying to help people. You're trying to help people follow your work always. So we're just going to put gauge pressure here. In which case we can say that pressure at C is equal to 0 because of C, gauge pressure. Great. So now let's simplify that. We say that PB is equal to rho G YC. That's not PA yet, but we can also use rule number one to say that PB equals PA, which equals rho G YC. So that's a really simple application of the Pascal's law, I guess is what it's called, but the pressure equation, pressure versus height equation. A couple of notes. Your book, and I'm not a big fan of this, but your book is going to say things a little bit differently. They like to, instead of rho G here, they like to use gamma, where gamma is just equal to rho times G, and it's called the specific weight. Now that nomenclature comes from the fact that this is a mass per volume. So L cubed, actually, let's just do L cubed. This is a mass per volume times gravity. So this is technically the weight, and then specific means per volume. So mass times gravity per volume. So that's why it's called specific weight. So your book will use that a lot, and you just got to remember that the gamma is just rho times G. Rho for whatever fluid you're using. I forgot to put in the O's here. Normally that's something people would yell at me about. Great. So that's that problem. Just a side note about gauge versus absolute pressure. Answer this quiz, this mini little quiz right here. Can gauge pressure be negative? Circle yes or no. And then also answer the question of can absolute pressure, can it be absolute? Can absolute pressure be absolute? Yes, of course. Can absolute pressure be negative? Okay, so hopefully you've had a chance to answer. The answer to this is yes, because gauge pressure is just whatever your absolute pressure is minus P atmospheric. So if pressure absolute is less than P atmospheric, then you end up with a negative number. And then can absolute pressure be negative? And the answer to that is no. Absolute pressure cannot be negative. There are thermodynamic definitions of pressure that can end up being negative, but for our purposes, pressure can never be negative. Great. So what if we have different fluids, like a gas and a liquid? And this is usually where manometers get used, is for measuring the pressure in a gas. So what if we have a pressure at A in this container with air, which has a density of 1.2 kilograms per meter cubed. And then we have this, and it's at a height y3. We have a height y1 where it's filled with water with a density of 1,000 kilograms per meter cubed, which goes to a height of y2 on the other end of this U-shaped manometer. We're going to use our coordinate system here where we're going to put y1 as 0. That's our 0, that's our datum. And we want to know what is the pressure at A and what model should we use. So the models we only have 2 models right now, are rule number 1 and the delta P is equal to rho G delta H, right? Or you might say P1 minus P2 is equal to rho G H2 minus H1. Cool. So we'll call this equation 1. And we're going to tell our graders that equation 1 was converted into equation 2 here, where we say that P1 minus, and that's P here, this would be P1. P1 minus PA is equal to rho A times G times Y3 minus Y1. So, let's make that capital A just so it's clear. What we're saying is that the pressure difference between this height and this height is just equal to this equation here. And we can solve this to say that P1 is equal to rho AG times Y3, because Y1 is just equal to 0, plus PA. So the next step is, well, we can go from P1 now to P2 using a different fluid. Because remember, you can only use this equation in a single fluid, right? So since we had air and water, we have to use it twice. Each time we cross a fluid, we have to use it, create a new equation. So we're going to go from, well, that was 2 to 3 here. So we're going to go from equation 1 to equation 4. We're going to say that P2 minus P1 is equal to rho water times G times Y1 minus Y2. So in this case, though, we're going to use gauge pressure, so we had to write our assumptions. Static fluid, B, density is equal to a constant, and C, gauge pressure, just to, like I said, make it easy on the graders. So since it's gauge pressure, P2 is going to be equal to 0, and that's because of C. We have rho water, Y1 minus Y2. Y1 is equal to 0. So we end up getting that 4 to 5. P1 is equal to rho water G Y2. Cool. So now we have 2 equations where we have P1. So we're going to take 3 plus 5. And this is, hopefully now you can see where the numbering becomes useful. Because now you're telling people I've got 2 separate equations that are on different parts of the page, and I'm bringing them together here. 3 plus 5 into equation 6 gives us, we're going to set these 2 equal to each other because they're both equal to P1. Rho A G Y3 plus PA is equal to rho WG Y2. And we know rho A, G, Y3, rho WG, and Y2. And the only thing we don't know is PA, which means we're done. We just have to plug stuff in. So we're going to plug stuff in, and we get that PA is equal to PA PA is equal to, sorry, I got distracted for a second, 1,000 kilograms per meter cubed times 9.8 meters per second times 10.2 meters minus 1.2 kilogram per meter cubed times 9.8 meters per second times 2 meters. So that tells us that PA is equal to about 100 kilopascals gauge, or 201.3 kilopascals absolute. Just a quick, oh, by the way, this is also about 2 bar, right? Because 1 bar is 1 atmosphere. Cool. Quick note, this is our air component, and this is our water component. What if I were to take the ratio of this, we'll call this little a, this is little b. What is b over a? It's about equal to what? Keep it integers. In fact, keep it powers of 10. I'll give you about a half second here. You can also pause the video, obviously. But if you look at it, everything's roughly the same, except for we have a huge difference in our densities, right? So B over A is about 1,000. So we have a 1,000-fold difference between these two pressures. And unless your precision and unless your accuracy that you're requiring in your measurement is better than 1 part in 1,000, guess what you can do? Well, that's kind of leading the question here. Can we neglect the air? The answer is yes. As long as H is small and you need low accuracy. So here's a question. If we only ever use 3 sig figs, do we ever care for more accuracy than 1 part in 1,000? No. Actually, 3 sig figs is usually about 1 part in 500 or 1 part in about 200. So as long as we're doing 3 sig figs, you can neglect air because it's will affect your answer less than the rounding error that occurs from using 3 sig figs. All right, so we're going to pause the video here because I want to start chunking these videos up into smaller videos. And then the next video, we'll start talking about the manometer rule, which allows tackling complex manometers more easily.